Now let's discuss about intrinsic semiconductors. These are pure semiconductors. For example, silicon, we discussed that it has valency of 4. So it will be making 4 bonds with neighboring atoms, right? So consider this structure of silicon. It is something same like what you have studied in the process of catenation in carbon atoms, right? So when this thing is happening, we have discussed about what? Conduction and valence band. So what is conduction band? I'll explain you. Suppose this electron here, okay, this electron breaks its bond and comes into free state. So this is an electron which is free from bonding, and what will be left? There will be a gap left. This gap is called hole. This hole is actually a positive charge, but this positive charge exists on the entire atom, because when an electron is taken out of the atom, the whole atom acquires an equal amount of positive charge, right? But in this chapter we are going to declare this as a separate entity, and this will be called hole. So right now I've got two charge carriers. One is this negative charge carrier, which is electron, and another one is this positive charge carrier, which is hole. So in pure semiconductors we have two different set of charge carriers, which are positive and negative, which are holes and electrons, right? Since the number of holes, suppose another electron broke its bond, is coming out of this state, so there will be another hole. So in intrinsic semiconductors, number of electrons will be exactly equal to number of holes, right? So charge density of electron is equal to charge density of holes. On basis of this fact, if I have to write the value of current for an intrinsic semiconductor, I can write this current as two different parts, that is electron current plus hole current. This is clear? Now we have studied a formula of current in terms of drift velocity, which is I is equal to NEAVD, right? So converting these two things, NEAVD plus NEAVD, right? This is charge density of electron, drift velocity of electron. This is charge density of hole and drift velocity of hole. This is just to make you clear that these are two different type of current. So in a semiconductor we have two different sets of current, which is electron current and hole current. Now if I take E and A common out, I'll be left with this thing, NEVE plus NHVH, right? This is I. If I take A on the denominator side, I'll be left with what? E and charge density, drift velocity plus charge density and drift velocity of hole. What is I upon A? I upon A is called current density charge per unit area. It is represented by J. So I'll mention it here. This is current density. I know I have a very bad handwriting. So J is E NEVE plus NHVH. Simple. Now I can replace J with another term. See what I'm doing. J, which is charge upon, no, current upon area. What is current? Voltage upon resistance, V upon R, according to Ohm's law. So this would be V upon R into A. I'm replacing V. What is potential? Electric field into distance, or electric field into length. So this V becomes E into L upon this R. R becomes rho L upon A. This becomes rho L over A times A. A gets cancelled out. This even L gets cancelled out. I'll be left with E over rho. So this J is equal to E upon rho. You have to note it down because I am going to rub that portion. So this whole thing is written as electric field upon what is rho? Resistivity, which is E NEVE plus NHVH, right? Okay. Now I want to write only 1 upon rho. What is rho? Resistivity. So 1 upon rho, that is reciprocal of resistivity, would be called conductivity. So I am taking this electric field on the denominator side. I am left with 1 upon rho, which is conductivity represented by sigma. And I have this electric field down here, which is NEVE and NHVH. This is all we have left. Now sigma is E. I am taking this electric field inside the bracket. That means I can write it like this. See, you have to do it in separate steps. I'm showing it here. I can do it like this. I can take this entire here. But instead of doing it like this, I'm taking this electric field separately for both of these terms, right? Simple maths. So let's do it. This was here E NEVE upon E plus NH VH over E. Why I did so? Because what is this? Drift velocity upon electric field. So drift velocity per unit electric field is called mobility. So mobility is mu. So sigma, which is E, Ne mu E plus NH mu H. This is the final equation of relation between mobility and conductivity in case of semiconductor. So what are the terms which we have used here? One was current density, another one is this, which is conductivity, and lastly drift velocity per unit electric field, which is mobility, right? Note this expression please.